Welcome to Deep Learning for Text Data. For this topic, we are going to focus on processing textual information such as number, text, sequence of words or letters, aka the NLP, which is natural language processing. So there are many possible applications and we can have document processing. So given a set of phrases, can you tell me its main idea? Maybe this is good to make your search better for your, let's say, document repository. Time series forecasting, given the past record, what would be the likelihood? Is it going to be raining or not? Right? Sentiment analysis, it can grab the if it's a positive, neutral, or negative sentiment based from text. So let's say the likelihood of Biden getting elected, right, are is most of the if that is the text written in a positive note or negative. So this is also useful when you're getting feedback from, let's say, your customers or let's say course evaluation from students, and you can basically do a sentiment analysis so that you could put a number, right, for those text data to see if most of the students do have a positive feedback or not at all, right? Next is sequence to sequence learning. It's a Q&A type of system or dialogue generation such as chatbot or word translation. So what is NLP? So it's a multidisciplinary subject where we have computer science, AI, linguistics. Okay. The primary purpose is to understand the context of the sequence of text, and by using algorithms and utilizing the methods specialized in knowledge domains, right? We have different AI models in the deep learning for image, and we can apply the same principles that we've learned for the text, right? Um, it is a challenging task to fully understand because for humans, it is unclear when it is blue or versus I'm feeling blue, right? It is blue is saying that it's a color, and I'm feeling blue means you're sad or down, right? So a simple like sampler for NLP could be spell checking, autocomplete, doing synonyms. So Grammarly, basically a software, a Chrome extension as well, provides this, right? It's very helpful when you're typing in the browser. Next is more complex example, right? You could have the question for language machine translation, like Google Translate, right? Sentiment of words. Actual application includes a search engine where it can do predicted text after it gets a minimum set of words. Let's say after 2 words or 3 characters, then it would do predictions, right? Sentiment analysis on social media network on politics or marketing, right? So that gives the let's say the marketer to get some feedback or if they're getting the correct feedback that they want, right? So if you think about deep learning networks covered, they are learning methods based on human designed specified representation of input training set describing the your real world. Okay, so apply DL on text as well, right? So the terms and definitions that we have, right? So we have this uh, system talk, right? When we say body of text, we call that as a corpus. The units that the network segments and associates into a numerical vector is a token, right? Tokenization is breaking the text into units. Vectorization is transforming text into numeric tensors. So this is like a vector of numbers, right? An array of numbers. There are two main techniques called the one-hot encoding and the text embedding. So for DL for NLP, right, is essentially the same pattern, right? There's word, sentence, paragraph. So for image, we have pixel, lines, edges, corners. So we do have these features that we can highlight or basically don't highlight, right? And that's how we can get features, okay? So one of the challenge for NLP is that image consists of a bunch of numbers but not words. Therefore, mapping a process of words numbers should take place before the DL to compute. This requires tokenization during the vectorization process, right? So if you have the text, the cat sat on the mat, you can create the tokens, which meaning what are the words. We have the cat sat on the mat, right? Then we want to do a vector association, and for the first letter, we have the 0, 0.0, 0.5, and 1.0, right? So each of them would have this vector, right? This series of numbers. For cat, we have 0, 0.0, 1.0, and 0.2, and so on and so forth. So tokenization is a type of text segmentation or lexical analysis which can transform a given body of text into characters or words or n-grams. When we say n-grams, it means number of you can say words or items, right? Um, so n or fewer groups of consecutive words or characters. I'll give an example of n-grams. Let's say the title is working with text data. If we have a 1 gram, it's going to be working, and then we have with, then we have text, then we have data. If we have 2 grams, we have working with, and then with text, and then text data, right? So those are examples. So we can go more with that, right? So going to the next bullet point, we have raw text as an input, and the matrix with your pandas data frame. Your data frame, think of about your rows and columns, so that you can create that 2D that dimension, right? And then we can use the Keras network. So in one-hot encoding, right, it's one of the vectorization techniques, and the other one is the token embedding, right? The one-hot encoding creates a tensor that consists of every word and its unique index, so it grabs unique words or characters, right? And then label to vectors, right? This was allowed to turn categorical data into the features, right? So we want to convert that category to features with numerical values, which are zeros and ones stored in a vector. The size of the vector is the size of the number of units, words or characters, of the input sentences. So here's an example. Let's say we have two elements, right? We have one string that says I study at CDU, and the second string is I study at CDU at Seattle, right? So if we get the word index, meaning the unique words, we have I study at CDU Seattle. Those are the not getting the unique. I mean, we just store one of each instance of the letter or the word, right? Okay. Then we basically transform them in, as you can see, an array of numbers, which is a vector, right? The matrix. So here's an example code of one-hot encoding in Keras, right? You have the sample, right? A list of two strings, right? Then you have the tokenizer, right? And you want to use the sample to fit on text as a parameter to your tokenizer, and then create the sequences. And then for the results, we want to tokenize and put that to a matrix, right? And then you want to have the tokenizer.word index and store that in your variable. You can read upon the comments here, and as you can see, the three printouts. The one is it grabs the unique token from the samples, right? And now it associated numerical values for those words, right? So it used the I as number 2, the study as number 3, and at as number 1, and 4 as city U, right? Correct. So we have this 1, 2, 3, 4, 5 as the word index. And then for the going back down there, the sequences, right? The next list of numbers, right, or integers, we have 2, 3, 1, 4, which is I study at CDU, and then you see the 1 again because that's the same word with the same index, which is 1, so at, and then 5 is Seattle. And then if you see the word index, these are the indexes that associate with that word. So you have the key at and the value, which is the index. Okay. So in token embedding, yeah, The second one, so in one hot encoding, it consists of many wasted unused spots, right, in the matrix. And the n-dimensional tensor, where n number of words in the vocabulary, token embedding uses tokenized vectors via hot encoding and produces lower but dense vectors with floating values that are learned from data. Learning or training word just like the weights are being learned in the previous networks we covered, right? Loading pre-trained word embedding to solve a machine learning task, right? If you go on the top right, there's the differences. Um, One hot is sparse, high dimensional, hard coded, and word embeddings is dense, lower dimensional, and learn from data. Okay, so the primary goal, right, of token embedding is to create relationship between words. For example, we have cold. It is an opposite meaning of hot, but they are related when we have the word temperature. We do have the accurate and exact, and they are similarly related, right? If you have tiger and lion, they are more related than choosing the word tiger and rose. So we do want to capture this semantic relationship between words, which embedding is designed, right? It tries to create this geometric space, which is the embedding, so that the Euclidean distance can be calculated, right? And this is done in the embedding layer, right? So now we can compute words. If we have tiger plus lion, it becomes liger, right? We can also do some computation such as when there's a word king and you did subtract male, then it becomes a queen, right? We have the tiger and what's the union with the car, and both of them are in motion, right? So that creates the relationships, right? And now with the embedding layer, we have the vocabulary. Let's say we have man, woman, boy, girl, prince, princess, queen, king, monarch, and that becomes translated to a matrix, which we have using the one hot encode, right? As you can see, you have the binaries, ones and zeros, and you have the words, and you have the index, right? Now, once we head on to the embedding layer, and then we create this new dimension, now we are able to get features out of it, right? So let's say for femininity, right, we have the woman, girl, princess, and queen, right? And monarch could be half and half, right? For let's say youth, we have the boy, girl, prince, princess, right? Royalty, we have the prince to the monarch, right? So again, this embedding layer allows us to featurize representation for word operation, right? Okay, so we discussed the other ones, right? And they now give you a prediction, right? So femininity, right? It's more likely for a prince, queen, and girl woman, and less on a prince, boy, king, man, and with the youth as well, right? So, token embedding example. So, let's say you have this sample, right? And then you want to print out the one hot representation, and you would see a bunch of these numbers, right? And you can see again for let's say the letter I, right? The number, the index that is associated with it is 7106, right? So this is similar to the 2341 we had earlier. Okay, now once we have this one hot encoding representation or results, we can now use the TensorFlow Keras to use the embedding part, right? And then now we can embed and now create this embedded, right, where we add the zeros as well, right? So now we can have this this vectorized output. Okay, so here's another example when we run that and compile, and we do have the similar output. And if you have downloaded the PPT, please check this embedding that Python notebook file, right? And run the following and do check like the prediction, right? So using a pre-trained network, right? GLOVE is an unsupervised learning algorithm for obtaining vector representations for words. Training is performed on aggregate global word-to-word co-occurrence statistics from a body of text, and the resulting representation showcase interesting linear substructures of the word vector space, right? So in the second bullet point, let's say we have a globe dot 6b and globe dot 6b dot 50d dot text, right? It shows 50 feature dimensional weights per given words from the training. Right? For example, where, not, this, and etc. Right? These coefficients are the ways to be used at the embedding layer, as in weights, right? And as you can see with the highlight of the red circle here, the where, not, and this. Okay. And so going back, the where has 50 feature dimensional weights, right? And the not and the this. So using a pre-trained network, right? Let's say we open up the text that we want to read and specify that it has the encoding, the UTF-8, right? We parse per line, and basically we try to get the coefficients, right? And basically store those coefficient as an index for each of the word in the dictionary, or yep, or in the data structure that was used for the words. And then we can print out the loaded word vectors and the length of the embeddings index, right? Now, once we done that, now we have to create a weight matrix, right? And we can do so with the following, with the embedding matrix, and then parsing the iterating over the t word index dot items, right? Grabbing the word and grabbing the index, right? And then creating this embedding vector, right? And now once we've done that, we can now start instantiating our model and do an embedding. Okay, and you can refer to the listing 6.10 to see this same example. Okay, so we've learned about the deep learning in textual analysis, right? So, and these are the references. If you guys have further questions, please don't hesitate to ask. And thank you very much for sticking with me for the 10 weeks. And I hope to see you again soon. And please stay connected. Till then.